I guess let me know if everybody can hear me so we can do the mic test ahead of time. Okay, good. Thank you.
Yep.
Oh, hey, Chris.
Hello.
Hey. Oh, I can hear you too. Okay, it's 9:05. Yeah, let's give it one more minute because usually what happens is I start speaking and then a few more people join in. And yeah, I guess we can start with an announcement. So it would be really great if all of you can join us tomorrow for the invited speaker talk. And this will be given by Dr. Ramona Vogt from Lawrence Livermore National Lab. And she's great. She gives a lot of talks and they're always very interesting. She's going to talk about fusion event generator that she personally works on with other people, which is Fire. And also she's going to talk about some of the applications of fission to other fields that we have not talked at all during this summer school. So one of the things that I know she's going to talk about is these astrophysics. So there is going to be some applications of that just to conclude the summer school with kind of a fun topic that you might not see a lot of in this school. So yeah, I hope to see you all tomorrow. And with that said, I think we have reached kind of the number of people that usually join. So I will start the presentation. And there we go. So this presentation here today is kind of a continuation of the presentations that I gave throughout the week. And also a continuation of one of the presentations that I gave maybe week 5, where I talked about time resolution, energy resolution, position resolution. And I hope you kind of had the opportunity to join that one as well. And today I'm gonna try to combine the theory that we discussed with respect to like what makes a good detector and the theory that we discussed throughout the past few days about what is fission, what are the questions that are still unanswered in fission. And we're going to talk about the actual practice. So how did people design detectors to investigate fission? And I'm going to look at a few types of detectors. I'm not going to look at all the types of detectors, but I try to divide them into the different parts, so into the different things that people look at when they discuss fission experiments. And as I said in the yesterday, when we talked about the active areas of research, we talked a lot about the computational models. So we said that there are some areas of research in which people simply are taking, well, it's not simple, but they are taking all the forces involved within a nucleus, all these strong forces and electromagnetic forces, and they try to model the movements of these nucleons that leads to the split. Or they can, they're trying to describe some very exotic modes of fission. So for example, very small nuclei or very large nuclei, neutron-rich or proton-rich, maybe induced by some weird type of radiation. And maybe they're trying to describe the neutron and gamma emission. And really all these different things, there are a lot of different models that can lead to this. And the best way to come up with new models or confirm the existing ones is to take experiments. So at the end of the day, really the most important thing is to really understand the fission products. So understanding what comes out of fission. If we want to understand how fission works, that's the best way. The best thing we can do is describe all the things that come out of it. And in order to study this, you cannot, well, some experiments you can do on like a tabletop experiment with a single detector, with a couple of detectors. But yeah, most of these things are actually already being done. So most of the things where you did 1 or 2 detectors and just a source in the center have already been done many decades ago. So now more expensive, more complicated or advanced. And so this is the reason why we look at the detectors built by large collaborations, either national collaborations, for example, the one you might find in national laboratories, Lawrence Livermore, Los Alamos, which I'm sure that you've heard a lot about in the past few days, or by international collaborations. So let's start with these 3 sections that I'm going to talk about. The first one is going to be neutron detector. The other two sections that I'm going to discuss are gamma ray detectors and fission fragment detectors. With that, I hope I can kind of cover the main products of fission. So there is charged particle, the charged fragments, there is the neutrons, and there is the gammas. There are, of course, a few more things that come out of it, but I'm not going to discuss them in this presentation. For example, you might think like neutrinos, antineutrinos are emitted, and charged particles are also emitted, but they might be similar to some of the things that were already discussed here. So first of all, the first type of a neutron detector that is currently being used to further our knowledge of fission and in general our knowledge of neutron emission are what we call neutron spectrometers. So spectroscopy, spectrum is of course the energy properties, the energy distribution of something. And the spectrometer is a meter or a sensor, a detector that investigates the energy of things. So a Neutron spectrometer is a specialized detector that is built in order to look at the spectrum or the energies of neutrons. To do that, and there are many different spectrometers, we employ this method called time of flight. And time of flight simply says that following these two equations that we have here on the bottom, we can find the energy of a neutron, and this is of course an approximation, classical approximation of the energy of a neutron, by finding how long it takes to travel a certain distance. So I know the distance the neutron must have traveled because I just have a source and a target and a detector, and I know how long it takes because I measured this time. And from that, I get the velocity. I know the mass of the neutron, so I can also get the energy. So in order to build a great neutron spectrometer, you need a very long flight path. Because while maybe the slower neutrons you are able to separate quite easily, as the neutrons get faster and faster, you won't be able to resolve two neutrons that come one after the other, maybe picoseconds apart, if your flight path is too small. For this purpose, you need to build a very long flight path. So the longest one that I'm aware of is the one at the ENTO facility at CERN, which is 185 meters. So that's an extremely long flight path in which neutrons are emitted, and then they have to travel 185 meters, hit a detector, and then that time difference between the emission and the detection is recorded. This type of detectors offer excellent energy resolution, kind of probably the best you can get for this purpose, but they suffer from very low efficiencies because you do have to wait until a neutron is emitted exactly in the direction. Imagine the solid angle that is covered by a detector 185 meters away. So you have to wait a very long time in order to get a single hit, a single detection, or you have to have a very large flux of neutron. In general, even if you have a large flux, you still have to wait a very long time. These are used for neutron energy measurements, as I said earlier. Now, let's say we are interested in the spectrum of things, but we're not only interested in that, and furthermore, we don't want to wait a very long time to get our results. One thing that we can do is to come a bit closer. So in this case, what we can do is instead of going 180 meters away, we come 1 meter away. And this is what they do at KNU at Los Alamos. And in this case, this system is also a Neutron spectrometer, but it's a Neutron spectrometer that offers many more characteristics of the neutrons. So for example, the distance of 1 meter is already good enough to give an approximately good spectrum of neutrons, but also because you have multiple detectors at multiple angles with respect to the source, now you can also find the direction of these particles. So you can characterize their velocity and the direction. So you can pretty much characterize all the kinematic variables that these neutrons have, as well as the correlations between them. These systems here, this KNU system and other systems similar to this, are usually used to find the spectra of particles, and also, for example, the spectra of particles when the angle made between two neutrons makes is a certain angle. So it's really good to investigate correlations in your data. This system here specifically employs, the KNU system specifically employs liquid organic scintillators, And as you know from the past lectures, you know that scintillators actually can detect both neutron and gamma rays. So this one here, this detector here, is kind of on the edge between a neutron detector and a gamma ray detector. And this is actually going to be the topic, the next section. So for gamma ray detectors, there are again two types that I find out. There are, of course, actually for neutron detectors, I didn't include another type of detector which was extremely common in the past. Let me actually talk about that for a second. I didn't include that because it's not so much in use anymore for discovering new things, but it's sometimes employed. And this would be large tank of scintillation material, or where neutrons, well, not scintillation material, of an absorption type reaction. In this case, what the purpose of this type of detectors would be to slow down the neutron until it reaches a very low energy in which it gets captured. These detectors are really good at finding the multiplicity of particles. However, because the neutron has to scatter along throughout the detector so much before it actually gets captured, you lose all the kinematic variables. So it's really hard to reconstruct any kind of initial direction or initial energy from these detectors here. So hopefully what these technologies here, these for example, the one that I have on this slide, the Kainu, we are able to reproduce some of these capabilities of these large tanks of finding the multiplicities of these reactions while maintaining also the kinematic variables of neutrons. Going to gamma ray detectors, I have divided into two sections. The first section is actually something that you will find throughout the world a lot. There is going to be a lot of collaborations, not just here in the US, but a few countries. I know also in Germany they have a few of these. These are called like gamma ray cluster detectors, or they investigate gamma ray clusters. And what I mean by that is that these detectors are made to detect as many gamma rays as possible following any type of reaction. This doesn't have to be fission specifically, but which is, however, an excellent example of a reaction in which many gamma rays are emitted. Could also be a neutron capture, in which a neutron gets captured by a nucleus, and then this nucleus starts emitting gamma rays to the excite. Now, these detectors are usually characterized by very large detectors surrounding a source, and these detectors fully cover the source. So there is a lot of studies, actually geometrical studies, in finding out how exactly to perfectly tile a sphere around the source. And if you ever see a detector that has 162 or around that number of detectors, it's actually because there are some geometrical shapes that perfectly tile a sphere, and one of them has 162 points, vertices. So these type of detectors, as I said, you can find throughout the world. Some of them can be found, for example, at Lawrence Berkeley National Lab or Argonne National Lab, called the Gamma Sphere. This is the same one, where it's just reproduced in two different places. This is also featured in the movie The Hulk, if you've seen it, The Incredible Hulk, I think the second one. And yeah, so these are very popular detectors that are used for many types of applications, including fission. The second one is, which is also similar to this, is the dense detector at Los Alamos National Lab again. And of course, the first thing that they have in common is this full coverage of the source. And the second thing is these very thick detectors made of inorganic material. And I'm sure by now you know that inorganic materials are excellent for gamma ray studies, because they have a lot of electrons, a very high electron density, and therefore they have a higher chance of capturing the gammas. However, sometimes the gamma rays simply scatter through a few detectors and deposit all their energies. It's very hard for a gamma to escape this system, but it's not guaranteed that the gamma will deposit all their energy in a single detector. However, when it comes to finding how much energy is released in a reaction, or approximately how many gamma rays were emitted, these are very good detectors. And for this reason, they're also very useful in nuclear structure when we try to find perhaps the levels, the energy levels of certain systems. The second type of reaction, the second type of detector actually goes to try to correct for one of the things that we talked about earlier, which was the thing that the gamma rays can scatter a few times throughout. So even though we don't know exactly what was the energy of each gamma, we know very well what the total energy released was. Well, in this type of detectors, which we call the high resolution detectors, of course, this is not a technical name, but just a classification of detectors that have high resolution. The purpose of this is to perfectly define the energies of gamma rays, even individually. So we're less interested in finding multiplicities of them and more interested in finding exactly how many or how much energy was stored in each gamma, what was the energy of each gamma. And there are a few ways to do that. One way is perhaps to use calorimeters, which they can have to be cooled down to extremely low temperature, and then every small interaction can lead, they have an excellent energy resolution, so they can be used to perfectly identify the energies of interactions, or maybe some smarter techniques like anti-coincidence detectors, in which we only measure gamma rays that had a single interaction within the detector. So every time a gamma ray, and I show here one example, if a gamma ray interacts with the detector labeled here ABCD, and then interacts with any of the numbered detectors around them, we discard that event completely, because that means that not all the energy was deposited in the first interaction. And using this, we can significantly suppress background as well as any kind of non-full deposition event. Again, this type of detector are used to investigate the discrete structure of spectra, as well as, again, the nuclear structure. The last type of detector that I'm going to talk about today are the fragment detectors. And those are probably the most exciting, because those are the ones that usually get more complicated than anything else. And the first one is actually, I'm going to start with the easy one, and not the easiest one, because the easiest one is actually a subset of this one. But let's talk about a fragment spectrometer. So fragment spectrometer is actually a very similar, analogous to the neutron spectrometer. In this case, we use, again, a long flight path, but instead of measuring the time of flight of neutrons, we measure the time of flight of fragments. So what is good and what is actually easier about fragments with respect to neutrons is that fragments are heavily, not only charged, but they're heavily charged, meaning that they interact with anything we put on their path. So if we, for example, if you had a neutron, you can put a detector, but you don't know if that neutron is going to interact with the detector. It might pass through and leave nothing. Same thing with the gamma ray. But with a fragment and any kind of charged particle simply interact with things every time. They have this long range force, the electromagnetic force, that forces them to always interact. So you can put detectors around these sources and be guaranteed that these things are going to be interacting with them. This detector here that I show as an example of a fragment spectrometer is located again at Los Alamos. And yes, I have been to Los Alamos, and that's why a lot of these slides are heavy on the Los Alamos things. The spider here is what we call a two-arm spectrometer, in which the source is placed at the center, and we have to wait, again, like in the Newton, we have to wait until the fission until the direction of the fragments are correct. And we have to wait until the fragments travel exactly in the direction of these two detectors that you see, these two caps at the end of this cylinder, to the left and to the right. And as it travels throughout this path, there are several detectors that are in place. The first detector is a detector that simply tells us when the start time is. So in this case, we know exactly when the fission occurs. A second detector tells us at what time there is an interaction along the path. And this gives us a stop time. However, within the same detector, we also get the energy deposited within this thin film. So for example, this detector could be a thin slice of some material, for example, how much energy was deposited within this material. And because we know that in a visible way, we can also try to extrapolate or infer the charge of the fragment from the energy that was deposited. So that means that we don't only have access to the kinematic variable of the fragment, so we the kinetic energy and the direction, but we also have some idea So it looks like I lost the connection there for a second. I'm gonna reconnect. Sorry about that. Okay. Let me just make sure that everybody can hear me now. And
I can hear you.
Thank you, Chris.
I can hear you, Stefano. Yep.
Thank you, Chris. Okay. And so we were talking about this portion here, which I hope everybody can see. There we go. So as I said, we don't only have access to the kinematic properties of the fragments, but also to some extent to the internal properties such as the mass and the charge. So we kind of have a more complete picture of the fragments by using these spectrometers. And of course, because of everything that I said so far, these are usually used for investigating the masses, the kinetic energy yields, and as well as maybe used for the correlating the emission of Newton and gamma rays with the identity or with the properties of fragments. The next type of detector is actually a very exciting one. These are ion track detectors. These are kind of the, I don't know if you've seen one of these weeks. I think there was a history of some of the detectors, or at least like an introduction to the first radiation detectors, which were like the bubble chamber and the ion chambers and things like that. These are kind of like the last evolution of that, like the most advanced iteration of these types of detectors. And these detectors simply track the ions, and an ion is simply a charged particle, a charged particle. And in this case, the ion are the fragments, and we track the fragments as it moves through the detector. So in the other case, we just had the information at the beginning, at the end. We knew the distance that it traveled, the time that it took, but we didn't know what happened in the middle. In this case here, we can use detectors that are filled with gas with electric grids, electrified grids, and electric fields that are very sensitive to the position of the particles to reconstruct in almost 3 dimensions the position and the velocity of the particle. So we can kind of see a movie of the fragment as it moves in space. And this provides, of course, full kinematic variables. So it doesn't just tell us about the energy and the velocity and the direction, but it tells us the energy, the velocity, the direction at each point in time. And this is, of course, very important if we want to apply, for example, magnetic fields and make the particle, turn and access the charge of these particles from these curves. These are also used, for example, if you want to study again fragment yields, but they're also very important if you want to look at exotic fission reactions. What I mean by that is, for example, if we wanted to look at ternary fission, of course, the assumption in the fragment spectrometer is that there are only 2 particles emitted, or 2 fragments emitted in that case. But in this case here, you really have a complete picture of what is going on in the fission. You have all the reconstruction of the charged particles, not so much the uncharged particles like the neutron and the gamma rays, but for the charged particles, you would have them. And on top of that, you also have some correlations of the fragment, like you have some idea of the fragment angular correlations. What I mean by that is, for example, if I have an inducing beam of particles and I want to know how the 2 fragments are going to travel away from this beam, if maybe they're going to be traveling preferentially parallel to the beam or maybe preferentially perpendicular to it, these type of detectors are excellent for that because they can reconstruct the direction of the particles. The last type of detector is actually not a detector. I just wanted to mention that here because it's a way to look at fragments. And in this way, what this is reaccelerated fragments. So of course, when there is a fission reaction, the fragments are emitted by the nucleus, and then they deposit in some material, and they just stop there. But after that, they have still very important properties. Even if after they emit Newton and gamma rays, these fragments themselves are extremely interesting, not only because of their role in fission, they still have a lot of things to do after they emit the first Newtons and gamma rays, such as the delayed radiation that we talked about on Monday or Tuesday. But also because they are kind of in a weird area of the chart of nuclides. They still have what we call their neutron-rich nuclei. They are in this part of the chart of nucleus that's not very well explored, and it's very important to explore this part of the of the new chart. So one thing that can be done is to take a nucleus, and this is done, for example, at the Caribou, at facilities, also that take fragments created by a fission reaction and reaccelerate them. So they can be used to then study these fission fragments as if they were things that we could prepare in the lab. But the source in this case is fission. So this was not exactly a detector, but I wanted to include it just to let you know also these kind of systems are being used in the world to study fission fragments as well. And with that, actually, this was a shorter presentation, about half an hour. But yeah, so as usual, I think I will take questions now, and let me go to the chat. And also, okay, before I go again, I know that some more people have joined, and so again, please, tomorrow there is going to be a very interesting lecture by Ramona Vogt from Lawrence Livermore National Lab. So it would be great if all of you could join. And yeah, if you have questions, about any of the things that we discussed here today, or any of the things that we discussed in the past few weeks, yeah, this would be a great opportunity. And there is actually a question: can you elaborate more on how we can get neutron spectrum with Kainu and Lano? How is directional information related to neutron energy? That is very interesting question. So, okay, I'll start with the first one. So at Kainu, the source is placed at the center of this array, of this hemispherical array of detectors, and the beam kind of comes in the middle. So maybe actually I can share again the screen, and we can go to that slide. The source is placed at the center here, and the beam, if you can see my screen, here, the beam kind of comes in this direction here, and the source is placed right there. So what this does is that we can investigate, for example, the energies of the neutrons as a function of the angle that they make with the beam. So the angle that they make with the beam there. And this is, of course, something that you could also do with a single detector placed far away. The other thing you could do is also, of course, like that you cannot do with a single detector, is to look at, for example, what is the spectra when two neutrons are emitted. So in this case, you have a beam of particles incident on, for example, a uranium target here, and then you wait until you do see two neutrons in two different detectors. And then you can look at the spectra of those two neutrons specifically. In this case, I don't know if the question was maybe even more specific about like how exactly do you get the spectrum? Well, again, you would have a T0, so you would have a information to when the fission happens, and you do also have a T final. So again, you can do time of flight. So it's again the time of flight technique, just like you would do when you had a flight path of 180 meters. You just do it with a much shorter flight path of 1 meter, which is, however, pretty good. So most of the results that they get from these experiments do get into like evaluated data, and it's good enough for a lot of applications. So let me know if that answers your question, otherwise we can get back to that. I'll move on to the next question now. On the last slide, the chart of the nucleus like chart was a bit pixelated. What were the units related to the different colors? Oh yes. So let me share the screen again. So this is actually related to the system that I was showing. So the colors here relate to how many. This is a beam facility. So the Caribou is a user facility that can be used by anybody who wants to run an experiment. And this one here, this chart here actually is showing how many of these fragments they can provide to you. So for example, if you're interested in this entry here, which could be, the axis here, of course, the Newton number and the charge number. And if you're interested in a certain area or a certain exactly square, then you can check the colored list here and they can tell you how many of those are you expected to see per second. So this is the yield the Caribou can provide to you in terms of how many fragments per second they're expected to be. Of course, it's not up to them exactly. They have to wait until the fission creates them, and then there is going to be an accelerator facility that takes that fragment and gives it back to you. Okay, yeah. It looks like the less stable nuclei produce higher yields. Is that about right? I would say that most of what determines the yield from Caribou is actually the yield from fission, and yeah, so fission it really does create things that are in the very unstable region, because they're actually not produced forever. Like the fission happens and then they immediately lose some newtons and photons, but then they still want to de-excite a few more times to get to a stable place. But in these milliseconds or seconds that you do have pretty unstable stuff being created. And when fission happens, there is some regards to stability of the fragments, but it's mostly kind of random as to which fragments are created. There are some, of course, some effects as to some fragments are preferentially being emitted if they're more stable, but in some very unstable fragment can be emitted. And yeah, so you can have very exotic, very neutron-rich fragments being emitted that can be very interesting. So yeah, and it's very interesting also to look at what other what other fission reactions can create. So for example, these would be like a Californian fission reaction, but you could look at, for example, like uranium, plutonium, or even like something more exotic to really give you the yield of the fragments that you want to look at. All right, so we do maybe like two more minutes of question if there are any, and just a question out of topic. What's your opinion about ITER that has celebrated by official state leader about start of assembly? I did not know that. Is that well? So I'm not sure. So what I studied fusion. Fusion is something that I am not super familiar with. Like I've taken courses about fusion. I know about ITER. I know it's going to be very expensive, and I hope it works. But I don't know. I don't really have an opinion. I really hope it works. I think there are a lot of great people working on that. I didn't know that they started assembly. So when it's like today or one of these days, they started assembly. So yeah, I hope they actually, yeah, I hope that they get what they want to get out of this. Yeah, it's actually not too far from where I am right now. 28th of July. Okay, that's good. I hope it doesn't blow up. So, yeah, so I'm not really an opinion on that. I guess that it is going to be something that is going to take a few years to complete, and it's going to take a few years after that to get some results. But it's a great field to get into if you're interested in that.